A person moving in zero gravity feels a pitiful helplessness. One wrong move and you'll find yourself spinning wildly. Everyone becomes a baby again in outer space.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Oh, yeah, baby, Dr. Ulrich Hans Volter.
Professor Dr. Ulrich Hans Volter, German physicist, engineer, and former DFVLR astronaut.
DFVLR, I had to look this up. Deutsche Forschungs- und Versuchsanstalt für Luft- und Raumfahrt is DFVLR. Wow. And they changed their name in 1989 to the more familiar DLR, or the German Research Institute for Aviation and Spaceflight.
Yes, quite right.
Which, of course, we visited, didn't we?
Yeah, big time. Yeah.
We should definitely congratulate China and the United Arab Emirates.
Absolutely. Congratulations.
Successfully launched to Mars this week.
That was pretty exciting, wasn't it?
Very exciting. Hope on the old Japanese H2A on 19th July. And we had the Tianwen-1 on the Long March 5 on the 23rd of July.
And I'm hoping, Matt, that on the 30th of July, on the Atlas V, we will see the Americans launch Perseverance, Ingenuity. Just saying, throwing it out there.
Imagine that, Ingenuity, a helicopter on Mars.
Get to the chopper. Do you think that's what they'll sound like?
I think Perseverance might say that. Yes, the plutonium's been loaded onto Perseverance. How exciting is that?
Oh my God.
We might even this week see an Ariane 5 launch as well, with another one of those mission extension vehicles on board. So that's exciting.
Jeez. Load up the plutonium.
Jamie, this week it's all about gravity, or the lack of gravity.
Oh, yeah. Where do you stand on gravity?
Oh, very good, Jamie.
You like that?
That's very good.
Yeah, good that.
I've got a guest on this week, Jack van Loon.
Oh, yes. A Dutch legend.
He sent me a paper called Gravity Deprivation. Is it ethical for optimum physiology?
Oh, it's a good question.
Is it ethical to withhold gravity? No, it is not.
No, that's the conclusion.
Yes, it is technologically feasible and financially achievable, but most of all, it's unethical not to do so.
Technically, it's feasible.
And financially, it's achievable.
I think that's the lyrics there.
Turned it into a musical all of a sudden.
I mean, who wouldn't want to go to that at the West End?
As Werner von Braun said, we can lick gravity, but sometimes the paperwork is overwhelming.
I like it.
So, Jamie, let's have a chat about gravity and what we can do about it.
Finally.
We're going to hear why it's not acceptable ethically for astronauts to not have gravity. And I'm going to ask you a question, Jamie. If I was to sit here and say to you, Jamie, the radiation in space makes all your muscle decrease by 30% after only 100 days. The radiation is causing the astronauts to have impaired vision. Their hearts are changing shape and getting weaker. The blood is reducing in volume. The radiation is causing astronauts' heads to expand. The radiation is causing the bones to leach away and release calcium into all the soft organ tissues. The radiation is causing the immune system to go all wonky and massively compromised. You'd be absolutely terrified about going into space, right?
Well, yeah. I mean, I'd be scared anyway, getting on a bomb to go into space. I don't think I'd let it stop me. I mean, there are risks, but I could get hit over by a truck tomorrow on crossing a boring road.
But you've got to admit, if I frame it as if radiation is doing all those horrible things, it kind of makes you a lot more scared, doesn't it?
Yeah, exactly. It's more of a scary word, though, isn't it?
Yeah, but whereas gravity deprivation is absolutely doing all those things that I just told you. But not only that, of course, the hilarious thing is, of course, radiation is doing loads of horrible things up to you in space as well. So gravity is absolutely a disaster, and radiation is also a disaster. So what the hell are we going to do about the first one? Let's forget about radiation this week. We'll cover it on another week.
Okay. See you later, radiation.
What do we need to know? Well, we'll go back on some of the stuff that we've talked about on the podcast before. What do you think gravity is, Jamie? What do you think it is?
Well, I think it's the force that pulls us all down. It's the force that binds us together.
What do you think causes that force? Well, what did Newton think caused the force?
Well, that's a good question to start with. What did he say?
Oh, Newton was the kind of first person who got to grips with gravity and gave it a formula.
Yeah.
So he knew it was something to do with the masses. So the mass of the planet itself.
Absolutely, the size of something defines the strength of gravity. No.
Yeah, well, the mass of it, not necessarily the size, because of course.
Okay.
Mass. As we've heard, a grapefruit-sized black hole, like the one that might be lurking in the solar system, is
big gravity.
Has quite considerably more gravity than the Earth, which is considerably bigger in size than a grapefruit. So it's about mass. So something about mass. Einstein actually talked about something else. And Einstein, after thinking about this thing called the equivalence principle, which we've talked about before, but basically the equivalence principle can be framed like this. You can say, when you're inside a metal box being accelerated, you don't know whether it's gravity or acceleration that's causing you to sort of be stuck to the bottom of the elevator floor, if you see what I mean.
That's right. Yeah.
So there's nothing you can do. There's no experiment you can perform to see which one you're experiencing, gravity or acceleration, linear acceleration. Yes. And I'll put the emphasis on linear there because that's important. But yeah, going in a straight line, accelerating in a straight line, can't tell the difference between gravity and that. And it's from thinking about that he realized, actually, what if, just like when you're turning a corner in a car, you feel this fictitious force, i.e. you feel as though you're being pushed out of your seat. But actually what's happening is you're just carrying off in a straight direction. And the seat is actually pulling you back in because the car wants to go in another direction, and so the seat's having to push you round. So it's actually what's known as a fictitious force because because it's being seen from a different reference frame. One's an inertial reference frame and one's a non-inertial reference frame and frame of reference. And so Einstein started thinking about that and realized that maybe gravity was a fictitious force and that it was caused by space-time itself bending. So just like when as you go around a planet, you feel the gravitational force down to that planet because you're essentially going round this curved path, even though you can't see it because it's space-time being bent and not like a road. But that's essentially what's happening. And obviously the best way to sort of demonstrate that is the big heavy ball in the middle of a rubber sheet and ball bearings going in orbit around it and stuff like that.
One of my favourite experiments.
So, but what it does do is say, there is a way of trying to recreate gravity using acceleration instead, right? There is this equivalence principle. So you could fly in a straight line in a 1G spacecraft, a 1G spacecraft being a spacecraft that's continually accelerating at 1G. And then you'd stand on the floor of the spacecraft and it would feel just like Earth.
Yes.
And in actual fact, you'd be able to get across the solar system very fast, across the galaxy extremely fast. It would be actually a really good spacecraft. However, where on Earth you're going to get the fuel from?
There's the rub.
Most rocket engines only fire for a few minutes at best. And ion engines that fire for weeks and months, they're incredibly puny and pathetic. So nowhere near 1g of acceleration. So it's all a little bit depressing. You're not going to be able to do it like that, certainly not in any time soon. But there's another way, Jamie.
Oh, finally, a bit of good news.
And that is to spin.
Oh, yes. Bring on the spin.
We've all experienced fake gravity when you get on like a merry-go-round and you can feel yourself being pushed back into your seat or pushed back or having to hold on to something because you're feeling this force.
Yeah.
However, there are some downsides to this force. There isn't an equivalence with this force. There is definitely a way that you can tell that you're not experiencing gravity, and that is because you are spinning, basically. And of course, the big one that everyone talks about is the Coriolis Effect.
The Coriolis Effect.
And we did talk about this on episode 121 because we had it as Space Word of the Week.
We did.
We've got an Ariane launch this week. Flies from the CSG in French Guiana in Kourou, as you know. And the reason why it's down there in South America is because it's on the equator, and it's a really ace place to launch from because you can fly east and get the spin of the Earth, which at the equator is about 1,000 miles an hour.
1,000 miles an hour?
1,000 miles an hour. And so that gives you quite a bump to get to the necessary speed which you need to get to if you want to orbit the Earth, basically.
Yeah, that's right.
To orbit the Earth, you have to be going fast enough that as you fall, you keep missing the Earth itself, which is about 17,100 miles an hour at the International Space Station height. So that 1,000 mile an hour is a pretty useful little bump to get you to your 17,000 miles an hour required. So remember, when you're up on the International Space Station, it's not because you're far from Earth that you feel no gravity. In fact, gravity at the International Space Station is almost as high as it is on the Earth itself, on the surface of the Earth. It's not that much different. However, the reason why the astronauts feel as though there's microgravity is because they're falling. They're actually, the whole thing is falling towards Earth, but obviously it keeps missing it, which is best shown in that cannonball thing that Newton drew all those many years ago.
Many years ago.
Yes. Obviously astronauts get a whole bunch of artificial gravity when they rocket up in the first place. To get out the atmosphere, they go straight up and feel this 3G, 3 times gravity pushing them down into their seat because of the acceleration. But then they roll over and start to go, once they're out of the atmosphere, they start getting this speed up so that they can actually get up to this 17,000 miles an hour that is orbit. And the moment they switch off their engines, everything goes weightless. It's one of those great shots. The moment they stop accelerating, they go from feeling gravity to suddenly everything floating around in the spacecraft.
Oh, I just really want to experience that one day, Matt.
Yeah, it would be absolutely awesome, wouldn't it? So we know that it's possible. We know all these things work, but Coriolis is a weird one. So if we had Ariane 6, instead of going east, it decided that it was going to do a polar launch. In other words, go north. Now, the weird thing about that is it's going 1,000 miles an hour to start with. So as it takes off and starts flying north, it's already going 1,000 miles an hour in the easterly direction along with the spin of the Earth, right? So, as it flies, by the time it's got to New York is only going 766 miles an hour. So, if you think about it, the further north it goes, the more the Earth is dragging behind it. So, the rocket will appear to bend to the right. In fact, it does bend to the right. And in actual fact, that's why hurricanes will all rotate anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere because of this bending that's caused by the Coriolis effect, right? So even though that Coriolis effect is really a sort of fictitious force, it's to do with the frame of reference that you're looking at, it's still very real. It causes real
effects. Is that like when people say that the toilet, that when you water down a sink or a toilet goes another way in Australia to here?
Do you know what?
But that's not true, is it?
I think that it's a bit of an urban myth. I think like everything, there's an element of truth to it. I think that if you pulled the plug in your bath 1 billion times, there might be some statistical push towards it going anti-clockwise or clockwise, depending on which hemisphere you're in. But actually, I can't remember what the answer to that was. But yes, it's a little bit of an urban myth.
And let's not try that experiment, because we need to save water on this podcast. So a billion times might be too much.
Well, it's a classic one for chaos theory as well. Like any kind of initial condition is going to have much more of a relevance on it than the Coriolis effect.
Very true.
When you think about it, it's obviously a little bit silly.
Well, let's pay it no mind.
So linear acceleration in a rocket has given you all this gravity. But if you've got a rotating structure, like in the old sci-fis, that uses a centrifugal force. Or, put it another way, is actually the centripetal acceleration via a normal force in a non-rotating frame of reference. So, if I let me put it like a little bit more ridiculous. So, artificial gravity is created by a centripetal force. So, as you're moving in a circular path, the floor of this circular space station has to keep pushing you to stop you traveling in a straight line into space. So as you're sort of rotating, all the time the floor is pushing you towards the center to stop you flying off into space.
Yes.
But that actually feels like it's a force coming from the center. So the centripetal force is what's actually forcing you into the center. And the force is actually supplied by the floor of the spacecraft. And the centrifugal force is what you perceive in your rotating frame of reference as pointing towards downwards from the center of the spacecraft out to the hull.
Uh-huh.
So, yes, that's a perceived downward acceleration, equal in magnitude and opposite in direction, Newton's third law, to the centripetal acceleration. So that's what you're feeling. Centrifugal force is pushing you down onto the floor of the spacecraft. It's really the counterpart of the centripetal force of the hull stopping your body going in a straight line, just like the seat in your car when you were turning round the bend.
God damn. It's hurting my head again. And that's probably gravity. That's probably gravity.
When you kind of get used to it, you can understand it. But there are a bunch of annoying things that come with rotating structures. It's not the same. It doesn't have this equivalence to gravity, because you can easily tell you're on a rotating structure. Even on a massive rotating structure, you could tell that you were rotating. So there are some design parameters that have to be taken into consideration. How big do you have to make the structure for it to kind of really work? So to get the gravity, obviously there's only really two components. It's how fast you're spinning and how far from the center you are. So what is your spin rate? How many revolutions do you have to make? But then obviously how far away you are from the center also will determine what gravity you're feeling. Unlike gravity, the force is pushing from the center, proportional to the distance from the center of the habitat. So if you have it very small, say if the dimensions were only the height of me, so 2 meters, a radius of 2 meters, it would be a disaster, because right at the center where my head is, I'd be feeling no gravity, and down by my feet, I'd be feeling as though I was back on Earth. And of course, what would happen then? All the blood would be rushing down to my feet. So in that case, we know that a 2 meter radius is going to be absolutely useless. It's going to be, it's actually going to be dangerous rather than helpful.
Yes.
And you could, the equivalence, you could think of that as a sort of an equivalent to tidal forces. in terms of when you're near something like a grapefruit-sized black hole. When your head, if you were going head first, your head would be feeling a lot more gravity than your feet, and that is what would kind of start pulling you apart, spaghettifying you, in fact. So it's a bit like tidal forces, except the other way round in a centrifuge.
I love the way you said, Jamie, when you go towards a grapefruit-sized black hole, like
it's going to happen.
Like
Jamie.
It happened last. It's going to happen, is it?
It totally is. Come on, Jamie.
It's inevitable.
When we discover that Planet 9 is a grapefruit-sized black hole, we're both going to go, right?
Well, yeah. Who else is going to report it?
Exactly. What else? What else is the Patreon money for? If it's not for that mission.
Exactly.
I have to say,
shout out to the patrons.
Shout out to the patrons who have been pointing out all week that flying off to this proposed grapefruit-sized black hole is depressingly difficult. Even Voyager is only a small percentage of the way there. That's how big the solar system is. It's tricky. Damn it. Yeah, I know. And we think of Voyager as leaving the solar system. It hasn't anywhere near left the solar system. It's ridiculous.
Not at all.
So another effect, Jamie, is as the rotating structure goes round, it needs to be reasonably fast so that when you walk in the direction of the spin, you're not changing your gravity significantly. Because obviously if you walk in the direction of the spin or in the other direction of the spin, now you're changing the amount of gravity that you feel. So you could become heavier walking in one direction and lighter walking the other. Now, I don't know about you, but that's probably going to make you feel pretty sick.
A little bit queasy.
But nowhere near as bad as you will feel if you walk in the other direction at a right angle to the direction. And that's where the Coriolis really kicks in.
Ooh, yeah.
And if you move your head slightly to the side in that kind of direction, it could be that it really messes with the fluid in your inner ear and makes you basically vomit almost immediately. And,
don't talk to me about my inner ear. Problems we've had.
Are you the type of person that gets sick on fairground rides?
Not really on fairground rides, but yeah, it depends which one you're talking about. On the waltzer, I wouldn't probably feel too good, but yeah, I think I'm normally not too bad. Although, yeah, I think if I'm in a car, I can't read. For example, if I'm in the back of a car, I can't read because it makes me feel sick. Or on a train, as you found out when I tried to do the podcast notes, and then I ended up
you're not good, are you?
Throwing up in the toilet on the train.
In other words, you've got quite a sensitive vestibular system.
Only when I read, weirdly. Everything else is fine. Stick me on a boat, I'm all right.
Yeah.
I can go on a roller coaster.
I guess as long as you can see and your brain is able to sort of make sense of the information, isn't it?
Yeah. I'd probably be a rubbish astronaut because I reckon that they probably at some point have to read something.
Oh, yeah. Oh, yeah, no, absolutely. Yeah. No,
maybe a few instructions.
I know, but when you're on the space station, you're not experiencing any form of movement other than this falling, but you don't know you are falling. You're just
true.
So you might find you're okay, although of course
has anyone ever, when they video the astronauts arriving and meeting the others on the ISS, has anyone instantly thrown up? Because I think that would be me.
Well, I told you about that the senator that threw up, and they now name how sick you get because he just didn't stop being sick. He was just sick for the entire time. I think most astronauts are sick when they arrive. It's actually, when you first arrive at the International Space Station, it takes a few hours to even get close to not feeling absolutely awful.
My God, when they've got cameras shoved in their face, they must feel like, just give us half an hour at least.
Well, I think they do. They do get some time. They don't open the hatch immediately. There's quite a few procedures that need to happen. So,
True.
In the same way, they don't follow them into the toilet and watch them going for a poo.
We're just going to leave this. Just going to leave this rolling, Tim. Is that all right? Can you give us 5 minutes?
Yeah, but this whole spinning thing is going to be a problem. Now, we've talked about this with space habitat. So if you want to go back and listen to this more in depth, we were talking about how big things like the Stanford Torus had to be, and why they made them so big is so that you actually can create a reasonable sweet spot where it's not too bad. But a lot of experiments on Earth have suggested that anything that's more than one rotation per minute is going to make you sick. But there is some good news there in the fact that all those experiments, of course, have been done in Earth's gravity. So far, we've never built this experiment out in space. So it's hard to say whether that's the vestibular system reacting to the sort of angle that you're at compared to Earth's gravity itself, which you can't sort of shield against. It's all permeating. True. So it might mean that you can probably get people up to about 10 RPM if you train them. But 6 revolutions per minute seems to be would be hard. It'd be very difficult to get used to, but the health benefits might be actually really, really good. So a sweet spot might be something like 6 revolutions a minute with a 20 meter radius. Now, it has to be 20 meters because we've talked about that whole idea of if you're, it has to be significantly more than your height so that your body doesn't feel a difference between your head and your feet.
Yes.
When you're going round. So there is a sort of sweet spot comfort zone, and that I reckon would be about the minimum. But there's been a few designs, Jamie. Do you want to? There's probably the best of the designs is one called Nautilus X.
Oh, I like it already.
Which is the non-atmospheric universal transport intended for lengthy United States exploration. Now, that is some form of acronym right there.
It's good.
Nautilus
I'm into
X. So that's a rotating 12-meter diameter space station concept. You'll notice that's underneath my sweet spot of 20 meters. But, this is a space station that is, where you get to and it gives you some gravity at least. It's not the perfect solution, but it's one that's doable. So this was Mark Haldeman and Edward Henderson of the Technology Applications Assessment Team at NASA. They reckon that this would cost $3.7 billion to build, this spacecraft, and it was a sort of floating space station, a stopover point for astronauts. And it used off-the-shelf parts like the Bigelow inflatables and other sort of satellite components that are readily available, hence the cheap cost. I mean, that's a lot cheaper than the Orion capsule, for example.
That's a lot cheaper.
A lot cheaper. It would only take about 5 years to build, so slightly quicker than the International Space Station.
Nice.
And you'd have this 6.5 meter by wide and 14 meter long corridor that inside the hoop. So that would be like the hoop. So quite a bit smaller than the most people have seen this in 2001: A Space Odyssey, where he's going for his morning jog around the Taurus.
That's right.
It's obviously smaller than that one, but not much smaller. So the actual centrifuge itself is made from this inflatable structure, utilizing Hoberman sphere expandable structures.
Beautiful.
And the whole rotation would be caused by Hughes 376 spin stabilized ComSats. So that was quite cool. And they went further and said you could build a demonstrator that would hook on the side of the ISS. And
right.
Yeah, but this was only 9.1 meters in diameter, but it would only cost about maximum $143 million, which I think is pretty good, right? $143 million for the first centrifuge in space.
I'll take it.
Yeah. And it could be launched on a single Atlas V launch. Now, I have to say, the numbers are pretty disappointing. As in, if it was rotating at 10 revolutions a minute, which is the absolute maximum, I reckon, you'd have to be trained to be able to even cope with it at all. You'd only be getting 0.51 Gs. At 4 revolutions a minute, which would be pretty grim still, you'd only be getting 0.08 Gs version.
0.8, okay.
But that's better than nothing, and at least they could actually look at things like 8 revolutions a minute would give you sort of Mars gravity. So at least you could actually start to see what the hell's going to happen here.
True.
And a really interesting one is if you've got this system that you can speed up and slow down, when it picks people up from Mars, it keeps them at this 0.3 gravity rotation and slowly ramps it up as it goes towards Earth on the journey so that they slowly acclimatize back to Earth's gravity again and are ready to get off like nothing's ever happened, which is pretty cool, isn't it?
Perfect crime.
That all sort of came to an end in 2011, that research, and I haven't heard anything more about it. There was another paper called or realizing a 2001 Space Odyssey piloted spherical torus nuclear fusion propulsion by Craig H. Williams, Leonard A. Dutsinski et al.
Okay.
And that was another really cool vehicle, this time a massive Earth to Jupiter vehicle that refueled at Titan and stuff like this.
Yeah, it looks very good.
It is very, very cool. And it's got a crew compartment that's on sort of the end of a three modules that spin around. Almost looks like a weather vane. No, those sort of little weather vanes that you have on top of boats that measure wind speed.
That's true. It does. And the arms look like little golf tees.
They do, don't they? Or those lollipops.
Oh, yeah. I remember them.
So that's got 3 structures that spin around. So that's a 17-meter arm, and it only achieves 0.2 Earth gravity, with a rotation rate of 3.25. So that sounds pretty good. And of course, one of the reasons why they sort of gave that is the kind of sum up to all this is that no one really knows the effect of artificial gravity on humans' physiology. And so really the only way you can design a spaceship is to just base it on other side effects like this moving around and the Coriolis effect and this changing gravity as you move around and the difference between your head and your toes. You basically say, well, the minimum we want is 0.2 gravity, which is the same as lunar gravity, because that seems to be about the minimum that's required to give you locomotion, to be able to walk around and actually work properly. You need to be able to have a maximum walking speed that's a quarter of the maximum rim speed. So you need to be able to sort of factor that in. You need to think about this tangential Coriolis force. So you've got to be really careful about how, the height of your astronaut and how long the kind of spokes are of your torus. And so you end up with these kind of acceptable rotation speeds, which have got to be between 6 RPM and 10 RPM at the absolute most. And you kind of need a minimum spoke length of about 15 meters.
Yes.
So that kind of gives you the constraints, and it's difficult to build, but we need to do it, don't we?
I think we do.
I've got to give one last mention to, as I was researching this, I found a YouTuber called Small Stars, who has done a really cool one called the GLS, which is using starships. So it's called the Gravity Link Starship concept. And you have 3 starships, and the central starship, the big one of the starships, instead of having anything on board, it's just got truss, like lighting truss and all that we use. It's got that all just stuffed in it, and then you unload that, and it becomes the central hub of this wheel, and the truss becomes the spokes out to 2 other starships. And then the starships get hooked onto this truss, and then they can just use some of their fuel to get the thing spinning. And then the starships, of course, either end of the spokes, will have artificial gravity. And you can change this using the thrusters on the starships themselves, so that you can, build up gravity or reduce gravity on your way to Mars, or build it up on the way back home, all those kind of things. And so you've got complete control of your spin using the starships themselves. And I think it's a really, really interesting concept. So I'm going to put a link to that video in the show notes.
I really want to see that.
Yeah, it's really cool. It's really, really cool. And he's thought about quite a few things, and it, it's a really cool idea. Slightly better, I think, than the Mars Direct one, where they have a sort of cable connecting them. I like the truss idea because it seems to be slightly easier to slow yourself down and speed yourself up, and all the sort of things that you need to do, because you've got this solid link rather than a floppy cable between you and the thing. So, Jamie, do you want to listen to my interview with Jack? I
absolutely want nothing more. Let's roll it.
But I just got to say, this guy is he's essentially a doctor of gravity. And he works.
That's a hell of a title.
He works at STech. He's a sort of contributing scientist there. He's won multiple awards. He's worked in this area for a very, very long time. Highly respected expert. And he's won a few medals as well for his contributions to the field of gravitational and space life science research.
Incredible.
And awards for his books, The Generation and Applications of Extraterrestrial Environments on Earth. So,
jeez, is there nothing he can't do?
Well, when it comes to gravity, really nice bloke as well. I let him down on the first call because I made a Zoom mistake, shifting people around, but no, he was super happy to talk to me, and I was if we ever want to talk about gravity again, we have to get Jack back on. Really,
well, it's good job that he forgave you, Matt, because gravity doesn't forgive.
No, very unforgiving. So, Jamie, écoutez.
The Interplanetary Podcast, putting the ace back into space.
Right, so I'm joined on the podcast by Jack van Loon, who is from the Free University of Amsterdam. It is also a cooperating scientist at STech for ESA. It's absolutely fantastic to have you on the show, so welcome to the podcast.
You're welcome.
The paper that you sent start by describing the sort of problem that it sets out, I suppose, because it's certainly one that I'd not really given much thought to, but after reading the paper, it kind of definitely swung me round.
Yeah, well, actually, what we describe in the paper is basically whether it's ethical to expose people, and especially space workers, so employees of space agencies or private industries or whatever, if it's ethical to expose people for a long period to microgravity or to the lack of gravity. That is actually where the paper is about. And we know that although you always see these happy faces and smiling astronauts and people under free fall or microgravity condition, it is really not a healthy environment. And we know that since Salyut and Skylab times in the 70s, that when you don't have gravity, so for a long period of time, you lose bone, you lose muscle, your immune system is deprived, your cardiovascular system is deconditioned, your cognition deteriorates. Recently, you see changes in brain composition or morphology. There might be other cardiovascular things like thromboses and so on. So it's tendency towards. So it's, microgravity is not a healthy environment. And we had the thought like, okay, if I am an astronaut and I'm, employed by a space agency, it's a bit strange that you are exposed to these, unhealthy conditions. It's the same as you are, a radiation worker in a hospital or an industry or, a nuclear power plant. I mean, you need to be protected from a hostile environment. And our statement in that paper is that we do not do enough to protect space workers from a hostile environment, being microgravity. That's basically the message of that paper.
Yeah, was it really known how bad microgravity was, or is it something that over the course of the last few decades people have thought, oh, that's actually much worse than we thought, or has it always been known that it was pretty bad for you?
Well, to a certain extent, it has been known. That's what I said. Since Skylab and Solute times, we know about muscle and bone. That it's very well studied. But especially with the long duration space station missions, with people going up there for half a year, and the Russians, some of these cosmonauts have been out there for more than 1,000 days or nearly 1,000 days. So for these long duration missions, we know more and more what this does to a human body. And lately you have problems with vision, the VIP and SONS, the visual, well, it used to be called visual impairment due to intracranial pressure. And now it's called space associated neuro something disease. I forgot the acronym. Sorry, but it's I mean, these are really symptoms from long duration spaceflight, and I mean, it is most likely, very well likely, related to the lack of gravity to people. I mean, we are evolved as human beings, over millions of years or thousands of years, under a 1G gravity environment. This is where our body is used to live in, and we are adapted to this 1G environment. It is also not healthy if we would live in a 2G environment, because our bodies are not capable of coping with the long duration 2D environment, as we are not capable to cope with the long duration microgravity environment. We're not going to die immediately, but it's a very slow process. And one of the statements we have in that paper is, if you look into the International Space Station, for instance, people call about a life support system, which means that you can live in a certain environment, which means that you have a certain temperature, you have a certain pressure, you have oxygen, and so on. So you can live there. And our statement is that, I mean, in these space environments, you also need to provide gravity, because that is an essential part of what we need as a human being to live happy and healthy. And that is not provided, in space station, for instance, or, when going to Mars in a non-rotating spacecraft. Because even, I mean, you have some studies where, people are using on what is called countermeasures, which means that you try to counteract the effect of the lack of gravity. So astronauts train like 1.5, 2 hours a day, 5 days a week, to keep their body in shape. Yeah. And this is because one of them is because of the lack of gravity. So first of all, it costs like 10 hours per person a week. So that's a loss of efficiency in the whole system, because, you cannot do anything else. And I don't know how much an astronaut hour costs, but, it's probably more than I make in an hour. And also, it is not, all these countermeasures they are helpful, but they're not completely helpful to all the disadvantages this microgravity provides you. That is what I said, like these changes in the brain, changes in the cardiovascular system, and so on, are just, these are new things that popped up for the last years or even the last year, where people at NASA and ESA and other space agencies were not aware of. and there might be more things that we are not aware of, and I think it is unethical to expose space workers to such an environment. It's a bit strange, if I would apply for a job, and then the space agency says, "Yeah, come and work with me." I mean, yeah, you're gonna lose some bone and you're gonna lose some muscle. Maybe your cardiovascular system goes down. Your immune system is a bit deprived. Maybe your cognition goes down. But hey, come and work with us. And by the way, you also get a lot of space radiation and solar flares, whatever, when you work for me. It's a bit strange. So we should think about a means to counteract that, and one of the means is to provide them gravity.
So yeah, is there any kind of indication about how much gravity is going to be required to sort of get anywhere near a point where you're not having all these side effects?
No, I mean it is. There has some experiments done on mice, where they had mice in a small centrifuge in flight, where it seems, and we did some experiments with plants, where it seems that Mars G, so 0.38 G, might be somewhat similar to 1 G with plants. Moon G is more like microgravity with plants. With animals, you also see some relatively positive effects, working on Mars G. But for humans, we don't know anything, and that's another reason why we should have a large rotating spacecraft in low Earth orbit in LEO, because then we can do that work. Why do we need to go all the way to Mars to find out that 0.38 G is maybe not a very good and healthy conditions for human? We can do that in LEO, which is much safer because we are close by. If there's anything, we can quickly, within a couple of hours, we can land and be in a hospital if needed. And it is totally new technology. It is totally new science. So, it should also be very attractive for space agencies, from a scientific point of view, to learn about how the human body adapts to long duration Mars or Moon G, in a safe, relatively close by environment, being in a low Earth orbit.
Yeah, so obviously the NASA and ESA have built the International Space Station, and that's obviously at a huge cost, and they've obviously got other life support systems that presumably are extremely expensive. So what do you think it is? Because it's not really an unknown thing, the rotating spacecraft. It's been the dream of science fiction even before Apollo. So what is it that's, because I was left really bemused after reading the paper and some of the papers that were cited, that it was like, why has there not been more effort placed on building a rotating artificial gravitational spacecraft?
I think it's purely budget, but then you have to ask, and there's where the ethics kicks in. So what is the life of an astronaut worth? Yeah, I mean, are you willing to spend 10 or 20% more budget, but because that is about the amount of money you talk about, but more studies are needed to really identify how much more budget is needed to come up with a rotating spacecraft. But what is the cutoff? I mean, what do you accept as providing your space workers with an unhealthy environment? I mean, instead of providing a healthy environment and the cost involved. I mean, this is a discussion people need to have in the open, in where that cutoff lies. So I think it is not the technology, because in principle we could do it. There are some papers on how you could do it, and what you mentioned, it was actually the Russian space pioneer Tsiolkovsky, who came with a rotating spacecraft already in 1903. So, more than 115 years ago. So it is something which, has been around and around and around for years. To be developed. So it's a cost issue. But even with this cost issue, I mean, what's the benefit? First of all, you take better care of your employees. Secondly, if you go for commercial spaceflight, which, is now a lot of people are looking into that, if I would have a business model where I would expose my my customers, which pay, I don't know, 5 million, 10 million to be in space for 2 weeks. I mean, one of the disadvantages of being under microgravity for a long duration is that you get, space adaptation syndrome, so you can get sick. You feel awful being under microgravity for a long period of time. I mean, it doesn't seem to be like a good business model to pay 10 million to be sick for 2 weeks. I mean, so, also for these sort of environments, I think it's good to have a 1G in space environment so people can go there and feel normal and have the option to go, let's say, to the central part of it or whatever the configuration of such a spacecraft is, to be under weightlessness conditions. I'm not saying that weightlessness should be abandoned. No, but it should be it should be available for people to go there to do the things that you want to do, or to develop the technology you need to be exposed to under microgravity conditions and so on. So you can still do the work and the experiments like on the ISS, but the living conditions or your life support conditions is also providing gravity. So it's a budget issue, and by that I also hear from some colleague scientists discussing it. Some of them really like a sort of Pavlov reaction, say, yeah, but that's too expensive. Like that's the end of the discussion. No, it's not the end of the discussion. And if you look at what, for instance, nowadays the launch cost of SpaceX is, if you compare that to 5 years ago, whatever, it's like, I don't know, like 10 or 20% of the launch costs from 5 years ago, going with shuttle or another launcher. So yes, it's more expensive to build such a rotating spacecraft, bringing up things in orbit. But hey, you pay like 80% less per launch than 5 or 10 years ago. So maybe it's not that expensive after all.
Yeah, I mean, well, actually, that brings in a really good point. If you've got people like Elon Musk and all the sort of commercial players coming on board, which have, like you said, they've reduced launch cost by at least an order of magnitude. So it's kind of the excuse of expense has peeled away. And do NASA actually turn around to providers like SpaceX and say, okay, well, we've got to build an interplanetary transport system if we're going to go to places like Mars. You need to develop, purely for ethical reasons, if we're going there, we can't expect people to be in microgravity for 180 days or a year and then work on Mars where we have no idea what even, a third gravity is going to be like as well.
And we could have such an idea if we make this third, Mars gravity in a rotating spacecraft in LEO, in low Earth orbit. So we can gain experience in what happened if you are at a certain G condition for a longer period of time. How can you adapt? And this is stuff we can, we can start, tomorrow in thinking about it and engineering it and building it instead of going to Mars. I mean, we need to prepare. There's no landing party waiting for you when you come to Mars. So you have to be self-sufficient. But can you be self-sufficient, and how does this transition from microgravity if we're not going with a rotating spacecraft? So what happens if you are in microgravity for a year and then you come into Mars G without support? I mean, how does the body respond, and what can you and can't you do in that environment? And this is all research we can do in low Earth orbit.
Yeah, is this something that you would rather see people tackling this thing in low Earth orbit rather than, say, tackling it in lunar orbit? Because obviously there's only a certain amount of space stations that you can maintain. But yeah, I mean, what do you think is the kind of roadmap for a more ethical treatment of our astronauts?
There is no roadmap. It's not within what we know, what I know about the roadmap ESA and NASA is working on. A rotating spacecraft is not part of it. And I mean, they are working on thinking and working on smaller centrifuges, like centrifuges that could be incorporated in the, let's say, in the diameter of a regular spacecraft, like what you have now for ISS, for instance. It's what is the diameter? Let's say about 4 meters or something. So you can build a centrifuge in a 4-meter diameter system, but it is not providing a sufficient amount. Well, that's what we think. It's not providing a sufficient amount of gravity over the body, because if you have a centrifuge, such a small radius centrifuge, your feet are experience a much higher G level than your head, which is nearly in the center of rotation. So it doesn't provide any gravity force. And one of the most important sensing system of gravity is in your inner ear, is the vestibular system, and that is not properly exposed to gravity. So, and over your body, there's a huge gradient of gravity. So, it is not the gravity you would see on Earth. It's again a sort of countermeasure, which might work to a certain extent, and I think it definitely, from a scientific point of view, it is definitely worthwhile looking into, but I don't think it's a proper solution. And we are developing these countermeasures and doing science and providing grants and whatever for years now, spending millions, while we could also spend these millions in actually engineering and developing a large rotating spacecraft. And for sure, we know that a lot of these effects seen from space, I'm not talking about radiation, but a lot of these gravity-related effects will disappear because you provide them gravity. I mean, there's no discussion on well, shall we provide like 10% oxygen to astronauts? I mean, it will not kill them directly, but they still survive. No, we provide them 21% of oxygen because that's what we have on Earth. Why don't we do the same with gravity?
Yeah, I mean, it is really curious, actually. I mean, it was definitely reading that paper, that whole aspect of it, comparing it to other elements that you would take for granted, was quite surprising. And I guess it's because ever since the first man went into space, we've just treated that as a given that they're not going to have gravity. So one question that I've never seen really fully answered with astronauts that stay, particularly, for example, Scott Kelly, who stay on a long time on something like the ISS, is there severe long-term illnesses that are caused by the lack of gravity, or is it something that the body recovers from?
I think there is not too much evidence on that. I know 2 examples. One of them is some recent study by groups from the US as well as from Europe, looking into the brain morphology of astronauts and cosmonauts. And there you see in long duration missions, so astronauts, cosmonauts that have been up there for half a year, you see changes in brain morphology. I don't know for how long they will remain, when they are back on Earth. There's another study looking into bone morphology from a group from Dr. Ficot in Saint-Étienne in France. And she had shown that even after 1 year of return of cosmonauts, so 1 year at 1G again, you still see a decrease in bone strength and bone structure in these cosmonauts. So at least it takes a year, and you're not fully recovered after 1 year. So, and there might be other effects where people have not looked into it clearly. So I wouldn't be surprised that you find it, with other things as well. I mean, this visual impairment, which I mentioned earlier, I don't know how long that will remain with some of these astronauts. And again, I mean, we know how to solve it.
Yeah, no, absolutely. Yeah, I mean, with something like the ISS, has it lived up to your expectations in terms of research on something like this?
It's getting better. It is. as you know, we did. I'm from the shuttle. I'm an old guy. I'm from the shuttle era, doing experiments in Space Lab, and we also did some Russian experiments. So I was very glad, with ISS coming on. But what I do see in ISS, it is I call it, with these shuttles, it was. You prepare for it, you know when the launch is going to be, and you have to be ready with your experiment and with the hardware and everything involved at that particular year, at that particular month, at that particular day, at that particular hour. Yeah, you know when the thing is going to be launched, and you need to be ready. For ISS, which is a permanent station, when you're not ready for this launch, maybe you're ready for the next launch. So the urgency of really tight planning and getting things done in time is a bit more relaxed. So things somehow were, implemented slower. That was my feeling. And but what I see now for the last couple of years, and especially in the US, but also in Europe, it's coming. Is with these more commercial providers. They provide access to the ISS from, not through ESA or NASA, but more through commercial parties. And there, this speed is picked up again. So it doesn't take that long anymore to fly an experiment. But yeah, I'm a scientist from a university, so I need to have my funding through, governmental entities. So it's not that easy always to go via commercial providers. But I think it's a good development to have these commercial guys involved and to speed up the process of having your experiment flown.
Yeah. So is there any other sort of groups of people or other people like yourself who are pushing for that? Who are pushing really to say, like, enough is enough. We can't have astronauts exposed to microgravity all the time.
You have some other, I have some colleagues. We working on another, let's say a pre-step of this, what we call the human hypergravity habitat, which is basically a centrifuge on Earth, a 200-meter diameter rotating system for people to live in for weeks or months under a hypergravity, so higher than 1G condition. And in that system, we can already start to learn about what happens with a human being for a long time in a rotating environment, and in this case under hypergravity conditions. And this is let's say an initiative where some 70 to 80 scientists and engineers are interested in, to start with. But I know that many more people are interested in it, and we trying to see whether we find a way to get this realized, to get it funded and realized somewhere. So it is something people are interested in, but again, let's say for in-flight application, I think it's a budget issue, but and this needs to be reconsidered and looked into again, from an ethical point of view, from the medical issues we have, and also from the costs, again, by using commercial launchers and revisit the opportunity. And we have a space station now, but for how long? Maybe another 10 years or so. But if we want to have a rotating spacecraft, we should start engineering and thinking about it now, so we can replace the ISS in due time with a rotating spacecraft, and also not neglecting, the microgravity part of it, because that is needed also for scientific and technology reasons. We need a microgravity environment because it's a unique environment to do a lot of scientific research. Yeah, but from a human health and ethical point of view, we need to provide gravity.
Yeah, I really like that idea that you alluded to earlier on about a rotating spacecraft that has one level of it, of course, that would be at the gravity of Mars. So you kind of get the double whammy, don't you? You get keeping astronauts at human gravity, you get the experiments of what it might be like to live on Mars, and you get the microgravity in the center. So
Yeah.
It seems.
I mean, it is complicated, but on the other hand, I mean, I think it's also from a space agency or engineering point of view, it's a challenge. I think it's a very interesting thing to do.
Yeah, and I actually think that the pub. I mean, I don't think it would be a particularly hard sell to the public either. In terms of, this is what we want to do. It's quite an exciting project. I think probably for me, it seems more exciting than going back to the moon, if I'm honest. But so I don't. It seems it would be an easier sell. I mean, maybe it's just the fact that people haven't re-looked at the kind of economics of it now that launch cost is plummeting essentially.
Yeah, and is it what is the maybe also people associate space with microgravity, and maybe it's I don't know. I don't know what other reasons. We're now looking with some people. We're now looking into the pre and cons of having a rotating spacecraft from an engineering point of view, because most of these papers that has been published in the past, it was or talks from people was really the cost issue, but we wanted to. I mean, in this new paper we're working on, we really want to look into the technology, what the advantages and also the disadvantages are. If you have a 1G environment in flight, I mean, the nice thing of being under microgravity is that you can use the floors and the ceiling and the sides to do stuff. Yeah. While living in a 1G environment, you can only use the floor as to live on. I mean, so your surface area of living is increased under microgravity conditions because you can go anywhere. And so there's a disadvantage having a rotating spacecraft at a certain G level, because then you live on the floor all the time. And so this is a disadvantage of it, and you have probably more disadvantages if you compare that to a microgravity environment, but you also have use advantages also from an engineering point of view. I mean, all fluid systems that are involved with fluid lines and fluid physics, I mean, it's much easier to do that in a 1G environment. It's also much more reliable than under microgravity conditions. Convection you have in a rotating spacecraft, which you do not have in a free fall system. So I mean, there are all kind of technologies that are impacted being under microgravity or in a 1G or partial gravity environment.
Where's the best place for people to go and visit your work or to sort of delve deeper into all this?
If they want to read, if they just Google my name, then they find some papers and it's most. We always try to publish in open source journals. So I mean, people should be able to go there. One of the sites for the large centrifuge, which we think of, having it on Earth somewhere, is you have to go to the H3 facility, so Hotel 3 and then facility.eu, which is a website to describe this ground-based system with some reference to to other rotating spacecraft. So you can Google it, you'll find something.
Yeah, well, I'll find the links and stick them into the podcast notes. Is there anything else that you'd like to add in before I let you get on with your valuable evening?
No, I want to thank you for having the time listening to this, to our views on that, and I really hope it's picked up by entities like ESA, like NASA, like JAXA or CSA, whatever, to really look into this and to actually engineer and construct such a spacecraft, because again, I think it's unethical if we deprive our space workers and especially our governmental space workers from gravity.
Yeah, and I just think practically, I just cannot. For me, I just can't conceive of how, like you said, there is no team on the ground to welcome the astronauts as they land on Mars and and sort of their hideously weak bodies trying to even cope with small amount of gravity just seems to be almost a crazy endeavor. So I think, yeah, it's just the lack of research, isn't it? The lack of what gravity does to you and the lack of what radiation does to you just seems to be, we seem to be very much in the dark.
Yeah, and if you look at the combination of gravity or reduced gravity and radiation, again, this is also what we could do to a certain extent in LEO, although we're still protected by the Van Allen belt, of course. But yeah, we can start, looking into these combined effects of partial gravity and radiation, also making use of this rotating spacecraft. And this rotating spacecraft, we in principle could rotate on any speed, going from 1G to Moon G to Mars G, and we can expose a series of human subjects to these gravity levels for half a year or a year, whatever you want, and then we can look in these effects. So it's completely new science. It's a bit strange that we know quite a bit of how the human body responds to microgravity with start with Yuri Gagarin up till now. We know pretty well how the human body responds to microgravity for a long period of time, although there are still quite some things hidden, as we know from the last year. But we know very little about how the human body responds to any other G levels. 1G, of course, we know on Earth, but Moon G, there are only a couple of people that has been exposed to Moon G for hours or a couple of days. But Mars G, we don't know. 1.2G, we don't know. And I think there's a lot of it to be discovered. I mean, we are now in COVID area, it's an interesting thing that if you look into animal research, there's a lot of animal research done in centrifuges. So mice and rats and fish and snails and a lot of animals have been exposed to long duration hypergravity situation, really weeks or months. There has been done experiments on mice, for instance, that were challenged with rhinitis, so sort of let's call it sort of flu or whatever in these animals. And if you expose them to a high G environment, it was shown that they recover from this flu much sooner than animals that were at 1G conditions. So somehow gravity also have some beneficial or prophylactic effect to physiology. You see the same with Drosophila fruit flies that have been exposed to high G conditions for a long period of time, and these fruit flies were infected with some fungi. You see that the longevity of these animals was increased, so they lived longer while under hypergravity conditions. So maybe it's and also with rats and rabbits, you also see a reduced fat mass in these animals under hypergravity conditions. So also with the common problem of obesity, I mean, we can do very interesting work on ground, exposing people to high gravity conditions, and to see how it how your obesity is reduced under these conditions. I mean, especially the UK is one of the areas where you have a huge growth in obesity, in diabetes and obesity, and so this might be a new paradigm to be explored. I'm not saying that we have to live in a high G environment for the rest of your life, but at least it's a paradigm to to explore and to see what we can learn from it, and maybe find another cure or another mechanism to cope with diabetes and obesity.
Yeah, I mean, I suppose that gravity research that a rotating spacecraft could do as well, or even, like you said, the ground facility, actually, reveals the way that the human body works, or at least indicates something that we might not know. Because, I can't think for the life of me why being under extra gravity would make you recover from flu faster. But
that's a fact. I mean, it's and also, I mean, people are probably also for this podcast. And if I give presentations of this, I always use a nice picture of Superman. Superman in the original book. Superman could run faster and jump higher than a human being. And the reason for that is that Superman came from a planet called Krypton, and Krypton had a higher gravity, was a higher mass planet than Earth. So his cardiovascular and musculoskeletal system was adapted, was grown, was evolved, let's say, under a high gravity environment. So when he came to Earth, I mean, you could jump higher and run faster, the same as these astronauts did on the moon. For human beings, evaluated under 1G conditions, going to a low G environment. That was the same for Superman coming from Krypton and living on Earth. So, but there's what you see if you are exposed to a higher G environment. I mean, you probably increase bone strength, muscle strength. So also for athletics, about you have these what do you call that, height doping. So you go to live in mountains for a while before going into a major tournament to increase your hemoglobin and whatever. I mean, what happens if you do your training every day under 1.5 G? I mean, you probably get stronger. So, you could increase your athletic score and whatever you do. So it's also, it's an interesting area. So
I can imagine you getting funding from football clubs to do this.
Maybe, yeah. the NBA, or I don't know what.
trying to push their teams just that little bit further. Thank you. Really, thank you very much for coming on. It's a pleasure to speak to someone that's so learned and been there, and you've done a lot of work. And I absolutely encourage people to go out and read some of your papers. They're really, really, accessible as well. I really enjoyed reading the one that you sent over. I shall put it in the notes. And thank you very much for joining me.
And thank you very much for having an interest in this.
The Interplanetary Podcast is alive!
Cool, huh?
I mean, wow. Just incredible. Thank you so much, Jack.
I love the Dutch.
Me too.
Jamie, if people have enjoyed the show, how can they, like Bob and McCult666, who joined the patrons this week, join the patrons this week?
Well, firstly, welcome, Bob and McCult or McCulty666. Welcome to the clan. If you would like to know more about how you can join and how you can follow us on social media, even buy some merch, there's just one website, www.interplanetary.org.uk.
And without your help, and without the help of the glorious Spodcats, this would not be possible.
We'd be no one. We'd be out there on the streets.
Now, it's a double-edged sword with the patrons. Each time we get a new member, I get very excited and honoured, but I also get a little bit stressed that I can't let them down, Jamie.
No, there's a lot of pressure on you now, Matt. Not me, because I don't really do anything. But I mean, you fucking. That is a lot of pressure. Keep
pushing
it up.
Down.
I think you're doing very
pushing down on you. No man has spoke. Jamie, I've got to go. I've got to get back to the old marking awful dissertations now.
Oh, that sounds really boring. I'm off to Margate for the day to see my friend and buy some records.
Ooh, I'm off to Kent tomorrow.
We didn't plan this very well, did we?
Oh, that's a bit annoying, isn't it?
Yeah, we'll have to plan it. We'll have to keep talking to each other.
Yeah, maybe we should talk to each other.
Yeah, we don't like talking to each other outside the podcast, do we?
Good God, no.
Just a bit much.
This is purely a friendship made from
gravity alone.
Oh, social distancing, Jamie. What a bummer.
What a bummer. The podcast is ending. I'd like to wish everyone a lovely weekend.
Cheerio, Spodcats.
Bye-bye.
See you soon. Bye.